go back to the calculation of limits. And you remember that sometimes, and the topic is L'Hopital rule. Sounds topical. Topic sounds L'Hopital rule. When we are working with uncertainties, infinity, or 0 with the 0, two uncertainties, we can use this very useful, very effective L'Hopital rule. How does it work? If we have limit when x tends to x0 or arms to x0, u of x over v of x, so that we have one of these two types of uncertainties. This limit is equal limit x still tends to the x0, or the ratio between first derivatives of these two functions. If we have these two kinds of uncertainty, if this ratio keeps these one of these two given uncertainties, this limit is equal limit of x tends to x0, a second derivative of the second derivative. And we can calculate these derivatives until we got to the zeros, or maybe we got to a situation then the derivative doesn't have one of the derivatives doesn't have can't be differentiated at all. It's clear that u of x and v of x, they have to satisfy the condition, to satisfy the conditions of if they are continuous and if they are able to be differentiated. So how does this rule work? Let's consider 2 or 3 examples. Example 1. Example 1. We heard, as you remember, this limit sine f of x over x. If we put x equals 0 into these two both we can consider sine x as a u of x and x as a v of x. If we put x equals 0, we have uncertainty 0 of the 0. This limit equal over x, and x tends to 0, we can calculate limit x tends to the 0, derivative of sine of x over derivative of x. Take into account that we have to calculate derivatives separately. Derivative of the denominator and derivative of the numerator. If you remember, this one derivative is, we have limit cosine x, sine gives cosine, x equal 1. Now if we put x equals 0 into this formula, we have cosine of 0 over 1. You can check your, what is it, cosine of 0, I remember it, it is 1, and we have 1 over 1, and it is what? 1. It's very easy to calculate, you can notice. Okay. Example 2. Okay. I can take very easy examples. X tends to, for example, infinity minus x squared plus 3 over, I don't know, x plus 1, for example. Okay. If we put directly infinity instead of x, we have infinity cubed, it is infinity over infinity. And we have uncertainty. But we can use the L'Hopital rule. In this one, I put here it is equal. Limit x cubed minus x squared plus 3 over x plus 1. And I have to calculate separate derivatives. It gives me 3 squared minus 2x. 3 gives 0. Here I have 1. If I put limit x as an infinity, I have infinity minus something, and it is infinity. So very clear that it is infinity. And the last one example for this one topic. Of 3. Limit, for example, x tends to infinity, exponent raised to power x over x cubed, for example. As a previous one example, if you put x equals infinity into this formula, you can have e raised to power infinity over x infinity raised to power 3. You can see that we have infinity over the infinity. So we have to calculate its derivative. Limit derivative separately of the exponent, derivative of the x cubed, and it is limit. I dropped this x tends to infinity because I save my marker. Exponent gives exponent, x cubed gives 3x squared. If I put here infinity, I have still infinity, nothing changed. And I can use the second one, not 3 but prime of x. I can calculate also 1, I can use the L'Hopital rule also 1. And it is limit exponent 3 squared derivatives. It gives exponent 6x. And I have still infinity here. Next step. One more again. Derivative. It gives exponent over 6x limit, and it gives exponent over 6. Now if you put here x infinity, you have e raised to power infinity is infinity over 6, so it gives infinity. You can see that it is very easy to calculate limits using L'Hopital rule. What can we do? The last one example about L'Hopital rule. It is a little bit more complicated than these two previous, but you can notice that we can work with not only ratio, but with the product of the functions sometimes. And now we consider example 4. We have limit x tends to, for example, 0. And for example, I have sine x exponent minus x times that. And for example, we have these limits limit for example, we have limit logarithm x times what? Times 6, for example. Logarithm when x tends to 0. Okay, very easy at the first glance. But if I put x equals 0 into both of these functions, we have logarithm of 0 times 0. We know that logarithm of 0, it is kind of minus infinity, and we have minus infinity times 0. At the first glance, here L'Hopital rule doesn't work at all, but we can make a trick. We can turn this given one expression into quotient. For example, ln x over 1 over x. We can put x into the denominator, and it goes into denominator as a fraction. Now we can put here 0, and we have something like minus infinity over infinity. 1 over 0 is infinity, minus logarithm ln of x is minus infinity, so this one limit fit into the pattern or the L'Hopital rule. Fits into pattern, and we can use L'Hopital rule here. It is ln x tends to limit x tends to 0 ln x derivative over 1 over x derivative. You know that derivative of the ln gives you 1 over x. Derivative of 1 over x gives minus 1 over x squared. And we can calculate it as 1 over x squared, but minus so here so you can cancel x and x, and you have minus x here, minus x. Since that, then you put x equals 0, we have that limit x tends to 0 of minus x for x 0. Okay, so I think it's enough for L'Hopital rule. I give you some individual work, 2 or 3 examples. See you later.